So I'm going to give you a brief background of cartilage and the enzymes that we think are important in cartilage breakdown, a bit about the biology that we do know, a bit about the new biology that we've discovered, and what next. So you saw this cartoon this morning. Tim Corson presented it, and also I'll just let it run through. So osteoarthritis is this gradual loss of articular cartilage from our joints. It's a very slow, gradual process, and as Tim said, we do get changes in the bone, and in fact this loss of cartilage doesn't stop at the bone. The enzymes will also help begin to degrade the bone as well, so it's really quite a problem. And clinically, osteoarthritis is rather viewed as a sort of a single entity. But I think now what we know about the biology tells us there's actually a spectrum of disorders that ultimately all have the same end product. We lose cartilage and that disables the joint. And as you heard this morning from Kenny, osteoarthritis is not now an inevitable consequence of ageing, as we thought it was. It's not just wear and tear, and it is actually underpinned by distinct biological pathways. And now that we know that, we can then investigate that and hopefully find some clues as to how we might be able to benefit patients. And so, at the moment, this is still considered the only cure for osteoarthritis, is a joint replacement. And so what we're trying to do is to try and come up with treatments that can actually either at least postpone that or actually negate that completely. So cartilage is a really, really unique tissue. So I've been talking to people this morning. So cartilage doesn't have a blood supply, which you might be quite surprised about. So there's no blood supply in cartilage, and there's no nerves in cartilage. So the first question you might ask is, why do my joints hurt? And we don't really know the answer to that simple question. So cartilage is also very unique because most tissues of the body are made up of lots of different cells stuck together by a very small amount of what's called matrix, whereas cartilage is the exact opposite. So we only have one cell type in cartilage, there aren't many of them, and most of cartilage is what we call extracellular matrix, bits that kind of join things together. So it's a very, very unusual tissue, and it actually makes a whole host of proteins. And although this is a very contentious point, trust me on this, collagen is probably the most important protein in our cartilage. It provides structural strength, so it's a really, really important molecule. And osteoarthritis, and indeed rheumatoid, are characterised by the enzymes driving the breakdown of cartilage, collagen. And so collagen fibrils actually wind around each other in threes, and they make like a rope, a really strong structure. And there's evidence, going back in the literature, that once you lose collagen from your cartilage, it's essentially an irreversible step. Kenny suggested that there was capacity for repair, but most of us don't have that much capacity. So if you lose your collagen, the cartilage is in real trouble. And so in health, the collagen provides the structural strength, and in disease, once it starts to get compromised, it's broken down, then you're going to have a disease state. So it makes the loss of collagen a really key therapeutic target for us. We really want to understand that, and maybe we can stop it. Now cartilage is really important because all our bones actually start life as cartilage. As we grow, they get remodeled and they become mineralized into bone. And enzymes known as proteinases are vital for remodeling all our tissues. And so proteinases are simply proteins that break down other proteins, enzymes. And proteinases are really important, so 2% of our genes are actually proteinases, and as you can probably tell already, I like proteinases. I think they're really interesting molecules. So we've got a lot of them in our body, so we have to remodel all sorts of tissues as we grow, and we use all sorts of different enzymes. And these enzymes really can be viewed as biological scissors. They come in all shapes and sizes to do all these various things, to break down molecules and make them look different. And in disease, they're often considered as the villains of the piece. But actually, not all proteinases are bad. We need them in normal, healthy processes. In disease, it's simply wrong enzyme, wrong place, wrong time. So the same enzymes that allow our bones to grow and develop are probably the same enzymes that are breaking them down in disease, because they get switched back on when they shouldn't be. So enzymes called collagenases, so collagen-degrading enzymes, are the ones that break down collagen, and they were first described by looking at tadpoles and how they metamorphose into frogs. They've got a great big tail, and that gets completely remodeled away, so you get a frog. And what people did was, they took a tadpole tail, cut it off, stuck it on a gel of collagen, and you get this zone of lysis. The collagenase enzyme degrades to collagen. So that was quite a breakthrough discovery. And we know that collagen, here's the three molecules all wound together, and these letters are simply the building blocks of collagen. And evolution has been really clever, that there are only a few enzymes in the body, about 4, that can actually break down collagen, and they can only break it down at one point in the whole molecule. So about 1,000 building blocks in these strands, and only one point can the collagenase actually cut it. So evolutionary, once you've got your collagen, evolution has said, you're not going to lose it. You can't afford to lose it, so we'll have very few enzymes that can do that event. But once it does get cleaved, these strands then unwind and get broken down by all sorts of enzymes. And arthritis was the first disease that was associated with a collagenase enzyme back in 1969. And this discovery was about 1962. So we haven't known about them that long in the greater scheme of things. Now, about 20 years ago, and you don't need to worry about this too much, but I've put this up because Tim Corsten actually was the leader who helped to find out what the three-dimensional structure of these enzymes looked like. And back in those days we thought, oh, once we know what the enzymes look like, we can make all sorts of inhibitors, cure arthritis, get rich, and everything will be fine. And unfortunately, of course, that didn't happen. And the problem with these enzymes, and they're called MMPs, is that they all look rather the same. So this is the bit that actually does the degrading of the proteins, but they actually all look the same. So lots of MMPs, and they all look the same. So when you inhibit one, you tend to inhibit lots of others that you don't want to inhibit. So you get side effects. So they didn't work. So we have to rethink what we're doing. So how do we find a novel target? Well, it really is a bit of a needle in a haystack. And I've just put these two papers up. I'm not going to go into detail, but around about 2000, we made a discovery that these two different classes of enzyme, that's all you need to know, actually interact to drive collagen destruction. In those days, that's all we knew. This group of enzymes called serine proteases were important, but we had no idea which ones. It took us until 2010, so 10 years of research, predominantly funded by Arthritis Research UK, I'd add. We then came across this discovery, this enzyme called matriptase, that we thought, oh, we've actually found a really, really good target. So then we did some more research. And so what did we discover about the biology? Well, we now think that abnormally loading your joint generates the expression of this enzyme. And this enzyme is really quite unique in the fact that you can activate a receptor on our cells in cartilage, and that drives the expression of these enzymes. But this enzyme also activates these enzymes to give us the active collagenases. And as I've just said, once they're active, they break down the collagen and get damaged cartilage. So, the simple part of the whole story is, if we block the enzyme, we block all these events happening, we preserve the cartilage, hey presto. So that's where the simple part of the story finishes. And what we don't know, and it leads back to what Kenny was talking about, is if we preserve the cartilage, do we then allow repair to happen? And that's kind of the holy grail in a way. We don't know whether that will happen, but it's more likely to happen if we can stop damage continuing. So, how do we discover novel compounds to target the enzyme we want? So if we view the enzyme alone, and then where we want it to be, more of a pussycat rather than a tiger, what we've done is we can look at the three-dimensional structure of the enzyme we're interested in, and this bit in red is really like the jaws of the tiger. That's the bit that's actually cleaving the collagen. Well, not the collagen, that's the bit that's doing the action of this enzyme. So what we can do is, rather like getting false teeth, we can actually make an impression of what that active site looks like, and make an impression so we can then fit molecules, inhibitors, that actually fit the mouth of the enzyme, as it were. So we can then do some fancy modelling. So we can then model these compounds. I don't know whether you can just see them, but there's a compound lying in this mouth, in the jaws. And we can do that by fancy modelling and work out how well they fit. How well do those false teeth fit in that particular mouth? And this is just a blown-up version. So this is the protein, and this purple structure here is the inhibitor molecule. And then we can interrogate with databases how good a fit that is. Does it really fit in there or doesn't it? That's just one way we can do this. Now the other way It's a bit like thinking about when we take, you might have seen these ancestral programs where they get an ancestral skull and then 10 minutes later they kind of tell you what that person looked like. And the reason they can do that is because they know where all the muscles attach. And so they know what size and shape those muscles are likely to be for that particular skull. And then they can reconstruct it. Well, we can do very similar things if we know about molecules and useful compounds. So if this was a useful compound that we know inhibited our enzyme to some extent, what we can do is, again, we do some fancy modelling, and you're not allowed to ask me about this modelling because I don't know much about it myself. I'm an enzymologist. And you can generate a map of the space that this molecule fills in 3 dimensions. So it's very clever, and so we can then think about how we map that into the enzyme. And we can do some further really fancy stuff, and you get all these what are called field space points. So these are all points that this molecule occupies in 3 dimensions. And once we've got this, we can then use this information to interrogate databases of all the known compounds and chemicals that have ever been made by any pharmaceutical company that's in the library. And there are millions and millions of these structures. So we then interrogate them and ask the question, are there any out there that look exactly or look similar to this that we might be able to use as a starting point to develop a new drug? So that's pretty much what we've done. And if you get lucky, which we did, you can then do some assays to screen them to see how potent, how good an inhibitor they are, and whether they only inhibit the enzyme you want them to inhibit. So you don't need to worry about the data, but here, this red inhibitor is a much better inhibitor than all these. And so once you've got a decent inhibitor, you then test it against a whole range of other enzymes. And again, this compound here is much better against our enzyme, the tryptase, than it is against them. So it's reasonably potent, reasonably specific. So great, the next thing to do is to then test it in an animal model, which is called preclinical testing. So what we've done, and quite serendipitously, the compound that we're using is 1066. So the Norman Conquest, etc., etc. So what we do is we induce osteoarthritis in the mouse, where we inject saline into the joint, and you can see cartilage damage. So we're losing this red staining that Kazi was talking about this morning. Whereas in the 1066 treated, this joint looks really quite nice, well protected. Here there's a little bit of damage, but when we do the scores, our compound is protecting that joint significantly. So, based on that, we would suggest that our data strongly support the concept that if we can get a really good inhibitor of the tryptase, it should provide significant benefit for patients. So this is my sales pitch now. We want more money, of course, because that's going to cost a lot of money. We think the next phase is probably going to cost a couple of £1 million to do. And where are we now? Well, this is what's called the drug discovery pipeline. It starts off with lots of compounds, and you go along here. We've found a target, we've done some lead discovery, we've started to optimise it, we've done some preclinical testing. What we really need to do is a lot more of this so-called lead optimisation. Make that molecule so that ideally we can have it as a pill that we can take orally and stop disease. That's a big challenge because, as I said, our cartilage doesn't have a blood supply. So how the drug gets to your cartilage is a big ask, but one that medicinal chemistry might be able to address. So that's where we pretty much are. I just have to acknowledge the people who did the work, because obviously it wasn't me who did the work. So this is the team of people who did the work. Obviously the work was started off by Arthritis Research UK, and the MRC finally paid for the last lot of money. And I'll take any questions. Thank you.